Hello, my name is Winno Witteveen, and in this video, I will be taking you through this tool that I've been working on called prstools and show you what it can do and how you can use it yourself. So this tutorial is set up in such a way that you can follow along yourself, basically on any system, as long as you have access to a web browser. We'll be using computational resources via Google Colab, which is available if you have a Google account. And you should be able to run everything that I'm about to show you yourself. So I'm using publicly available tools and software for this. So we're starting out with a web browser, and then we're going to look for prstools. And first, unfortunately, we do not yet have a hit, but if we type in GitHub, you'll get the relevant GitHub that you can go to. Then here we have the landing page with a standard README. So normally you would install prstools using this particular pip install command, which requires you to have Python 3.8 or later installed. So that's if you want to install it on your own system. For this tutorial, we'll be scrolling down and be looking at the tutorial section, and we'll be having a look at the getting started tutorial. So if we click that link by opening a new tab and move to the tab, we'll get to see the contents and the examples we'll be working with today. So this is a so-called Jupyter Notebook, which is a web-based, mostly awesome Python interface that you can use to interact with Python via a web browser. And we don't want to be setting up this environment ourselves at the moment, but this can be easily accessed via Google Colab. So for this, you just have to click this link over here, which will open a new tab. And so now we have reached the place where we can actually do things, which is our Google Colab. We can run cells in this Google Colab Jupyter Notebook by pressing Shift-Enter. So let's go ahead and do that. First, we get a warning message. So this notebook was not authored by Google. So Google warns you that you're running code that isn't directly from Google itself, but comes from GitHub. In this case, we know where the code comes from, so we can click Run. And so you can actually step through all these examples that I'm about to show using a Shift-Enter and run all the relevant commands. But for this particular tutorial, we'll be using the terminal, which it also provides by clicking here, which gives a more realistic view or the example of what you're probably to encounter in a real scenario. So let us see. First of all, we need to install prstools. So that's done again with this pip command. So we type in pip install. So yeah, pip install is to install stuff inside of Python. And then we type in prstools -u. And this u is just to update the package in case it's already available inside of this particular Python. So we run this and it will start installing prstools. And what we see is that there's already a bunch of stuff available, but that also that it installed a bunch of the new stuff. So since this correctly installed, since it says successfully installed PetReader, Jedi, and prstools, we'll be able to type in the command prstools and we'll get this output. So now we will be focusing on a particular subcommand. So we can add these subcommands to prstools and then access these particular subcommands. So for instance, we type in prst, which is shorthand for prstools. So basically just means the same as writing full prstools. So prst, cs2. So now we get the help of this particular prstool command, which is a version of prcs that I created and called to here to distinguish it from the original version. And what we can see here is that with this help message that's printed here, we have general options, we have data arguments, and we have model arguments. And so of the data arguments, the first 5 are required, and of the model arguments, all are optional. And apart from this documentation, there are some examples at the bottom, which we'll now run. So first of all, before we can do anything, we need some data to actually run a PRS procedure. So we'll first copy this first line, which will go ahead and download a bunch of data, unpack it, and move into the example directory that we create using this tool, this line. So we use the download utility and say that it should download the example, and that the destination is going to be this particular directory, and that it should move into the newly created example directory. So running that, it's downloading something, unpacking it, and we're also moved into the directory. So if we now see with ls what's inside of this directory, we see that we have a LD reference, the sumstat, and a set of link files, which are our targets. So now we can look again at the example of the help and copy this little bit over here, which I'll walk you through. So we have the LD reference mentioned here, so the directory indicated with a --ref flag, the target, which points to the prefix of the link files. So in this case, you could also say target.bin, target.fun, or target.bet. The tool will figure out all by itself where the relevant files are, as long as one of these options are in the input. And so then we also need to supply the location of the sumstat file, which we do with the st option, and the GL sample size, which is optional in case there's actually a sample size column inside of the sumstat. And then lastly, we also need to say where the output should be stored. So that's going to be a directory optionally plus a file prefix, which will take to be results-prcs2. So let's go ahead and run this. So what we see is that, it basically shows you the options that it's using, where it's working, some general information about how it's configured, what it loaded, how it subsequently combined all this information. So in this case, the substat, the targets, and the reference, and that there was a large coverage of the reference. So this is actually an important number. So generally you want to have a good coverage of the reference. So the idea is that the reference is generally a very representative set of the genome. And so you would want the reference to have a lot of matched variance between the target and the sumstat. So generally we would like this number, this first number, to be close to 100, but we would definitely like it to be higher than 80. And if it's lower, then maybe there's an issue with the target or the sumstat. So one perhaps needs to see if one should use another sumstat, or perhaps the target needs to be imputed to have the hopmap tree snips. So now moving on to the model. So the model trained 1,000 iterations, saved the weight file, and subsequently also predicted the polygenic risk score for the target individuals. And so now if we look in our directory and see what we have, we can see that it has generated these 2 result files. And if we then have a quick look at what's in these result files, at the top, we can see that we have a file containing the polygenic risk score in the last column for the different individuals indicated by the FID and the IID, IDs, sample IDs. And we have, in addition to that, the weight files containing the weights that were learned by the procedure. So this now is a very general, basic example of what the tool can do, but perhaps not really a very realistic reflection of what one would encounter in the wild, so to speak. So for that, we'll now be moving on to the first real case study of a real PRS creation case. So just for starters with that, generally the sum stat needs to be in a very particular format, or one should supply additional options that would allow you to basically find the right column names for the things that the procedure needs. So if we have a quick look at what's inside the sum stat, we see that there is a SNP column, an A1, A2, a beta, and a p-value column. So there might be cases in which you have a file with very different column names, and there is a way, by giving an option to say, oh, actually there is a SNP column, but it's called RSID, or there's an A1 column, but it's called affect allele. And so we'll be going into how we can tell this tool to figure that out. So now we'll move into the main directory and be making a new directory that we'll call case A. So in this directory, we'll be doing our case study. We'll be moving into this case study directory. So as you see now, the directory is actually empty. And to start off, we are first going to see which sum stat we would actually like to use. So for that, we'll be going to GWAS catalog to select a nice sum stat we are interested in this particular case. And so today I'm feeling like I'm very interested in height. So I'm typing in height. And so just for a context, GWAS catalog contains GWAS summer statistics. And that's why I go there now, because it contains many of them, since many people submit theirs there. So now we have some options here, and we're interested in having full summer statistics. So we go ahead and click this full summer statistic button over here. And of course, we would like to have a large sample size. So we order by sample size and see which studies have a lot of samples included. So for this case, we would like to have a sample that is for one particular population, because we would like it to be matching with the reference we're going to use. So we'll, for now, select this version over here, because this seems to be a combination of many different ancestries, which is actually we can also work with. But for the initial simpler case, we'll have a look at this one over here. And so we would actually like to download the sum stat. So we'll go right ahead and click on the FTP download link. So and then just so we don't forget, the sample size is approximately 1.6 million. So then we go to the FTP downloads section. We see that there is a so-called harmonized section, which is nice, because then there's going to be some harmonization of the sum stats. And then we see that there are a bunch of small files, but then the biggest one is obviously going to be the sum stats. We copy the link, and then we move back to our terminal to go ahead and wget, i.e. downloads that sum stats. So for that, we copy the link after the wget and hit enter. So bam, now we actually have the GWAS sum stats. So if we then see what's inside, we see that unfortunately it's still zipped, but luckily our tool can actually deal with that. So we can actually already move on to the next step, which is to select a reference and a target data set. So for this, we'll use some data that I've already curated. So we'll use the download utility of prstools. So I'm going to type prst, download util. That's the tool. And then it gives you a bunch of options, as you see here. And in this case, I'm going to do --list, which will list the curated file set and their respective download links. So now we see a bunch of LD references and some example data and some other SNP related files, and we'll be first going for the target data set, which is going to be this last bit over here. We're going to download that and use that as our target data set. So to get that, we're going to type in --pattern and put in a string that will only match this particular tar file. And so if you then type in G1000 and hit enter, the tool will say a pattern was used which matched the following files, which in this case is only this g1000.tar.bz file. And so the download will not start because destination dir or des-dir was not specified. So if we then type that and make it the destination dir this directory, the tool will go ahead and start downloading. So downloading and unpacking. And so if you now type in ls and see the directory contents, we see that there is actually a G1000 directory now. So if you go ahead and see what's inside of the directory, you see that there are a bunch of link files again. And then now we would also like to have an LD reference. So for this, we'll be looking at our list again. And today we would like to have a look at the 1000 genomes European reference. We could also go for the UK Biobank European reference. But for this case, we'll be going for the 1000 genomes one. So for that, we'll be also using a pattern. So by the way, like to get these commands back, I'm just pushing the up button. That gives you the command back. And generally, you can use tab to autocomplete commands, or like directories, which can be helpful to type faster, in case you're not super familiar with command line. So now we'll type the string that's only matches this particular LD reference. So it's going to be 1kg _. So with this, we'll be only downloading this particular file and then packing it and creating an LD reference directory. So let us see, is the downloading going fast? Also in this particular Google Colab environment, your downloads can at times be very, very fast. Well, depending on what you're used to. Some people, might have download speeds that are even faster. But in this case, I think it could be worse. So I think there's no need to pause the video for this waiting time. So we're almost done. Yeah, and we're done. Thinking actually probably I should make this a little bit bigger. Yeah, and we're extracting. Less clutter. It's almost done unpacking. Yada yada yada. Righty. And so if you now look at the contents of the directory, you see that there is an LD reference directory as well. So now we can go ahead and type a similar command as we typed in previously, but now we can add the relevant options for this particular data set that we, or summer stats, target, and LD reference for which we want to generate PRSs. And so what we will do now is we type in PRST, PRSCS2, and then have the opportunity to see the different options again. Then we'll type in ls again, so we have the directory contents in front of our eyes. And then we'll go ahead and start putting in the different options that are required. So first we'll type in the reference. Also, you can use a shorthand, a -r, which is just simpler and easier, shorter type. So the reference is going to be the LD block 1kg per directory. And then we also need as input, of course, a summer statistic, which we just downloaded. So we're going to do -s and then the sum stat. And then we're going to have -t, which is target. We're going to input the D1000 directory, but then we need to actually see, what's inside of this directory. And it's, I'm typing tab, so it already autocompletes. And if we keep hitting tab, we see that there is this set again, right? And so now we can go ahead and type in, let's just bet, or just keep it like this. Let's do that. So now I'm feeling like fun. So you can do fun. And then we also need to specify our output destination. So for this, we'll be typing something special, which is also an option of prstools. You can actually use the different variables, the inputs that are in the activated options to generate file names. So what I mean with that is that if I now type in SST, then the output file name will be the sumstats file name. And if I type in ref, this part of the file name will be the LD reference core directory name. And then in addition to this, we can also inject the targets. So this will allow us to make composed output file names, which makes it harder for you to accidentally overwrite things that you don't want to overwrite. So yeah, that's something you can use if you want to. So let's hit enter. Oh, wait. And we should maybe in this case also specify the sample size. If we also incline, so 1.6 million. And so in Python, you can actually type it like this. So you can use the dashes as a spacing and make it like look a bit more clear. So now hitting enter. So something has actually happened, but there's an error. And so there's a bunch of text. And then if we scroll down, we see that we actually, let me quickly look at the time. And we see that there is an exception. Missing required columns, snip A1 and A2, alternative names, snip A1 and A2. Please add them. So there is this option call map that allows you to specify different call names. And so if we look up, we actually see that it was able to read the sumstat, but it was not able to recognize the relevant columns in this sumstat file. And so we here have a collection of original columns and current columns, and we can also see that they're all still the same. And so what call map allows you to do is basically say, okay, this is a call map. So look at my cursor, right? There are these standard column names, and we can actually say to the tool, okay, these column names are different in this particular way. So to make that a bit more concrete, we can go ahead and copy this piece of text, then push up to get the command back again, then paste this behind it, remove the is, and then go ahead and substitute the relevant column names into this standard string, so the default string. And so what we'll be doing here is we'll be basically saying, okay, snip, which column name contains the snips, the snip IDs. And in this case, we have the variant ID, but we also have RSID. And since the reference is made up of RSIDs, we would like to use RSIDs in this particular case. So we type in RSID. Then we would like to have the two different alleles. So we have effect allele and other allele. So that's going to be matching for A1 and A2. So we type in effect allele and other allele. For beta, we're going to have actually also beta, but lowercase. So we don't actually have an odds ratio in this case because it's continuous phenotype we're looking at. But the thing is we don't have to remove it. And if the column mapping cannot find the relevant column to transform into the odds ratio column, then it will just skip it. So in other words, if I type in nonsense, this will not negatively affect the procedure. It will just try to look for nonsense column, and it will not find it, and it will not do a translation into the odds ratio column. And so now we have a P. And so you can see if we actually have the P value in the substat, which obviously we have. So we type in the relevant name, which is going to be P_. value. SE is going to be the standard error. Do we have standard error? Yes, bingo, we have standard error. So we type in standard error. And then you can ask yourselves, do we also have sample size? And lo and behold, we do, which is simply lowercase n. So now we go ahead and run this and see what happens. So far, so good. It's definitely doing something. So it has loaded approximately 1.4 million variants for the relevant first two data types, like the sum set and the target. And then the reference file is 1.1 million. And then we see that after combining everything, there is a good coverage of the reference. So that's good. We wanted this number to be high, like close to 100. So that's the case. So we're happy about that. And now it's off doing the training of the PRS model. So in case of this particular reference, we're going to have 22 chromosomes times 1,000 iterations makes 22,000 iterations, which might take a while. But in our particular case, we might not want to wait for that. We want to have results relatively quickly. So we're going to Control-C this, stop this, and we'll be typing --n iter to give a different number of iterations, which will take to be 4 to make the procedure finish in a reasonable amount of time. So let's go ahead and hit enter. And so in this particular case, something I haven't talked about yet, we see that there is actually a number of workers specified here. So it's by default 4. And the number of workers times the number of CPUs is the number of cores the procedure will actually use. And so if there is a lot of computational work to be done, it's generally good to increase this number up to the number of chromosomes in the reference. So that's going to be 22, and only then increase the number of CPUs. So generally, if you make this number very, very high, then that's not going to lead to very good performance in terms of compute. So it's completely going to take a bunch longer. So generally, you want to increase the number of workers first, and only if you then still have a lot of compute cores left should you increase the number of CPUs. So the procedure has finished, so we can have a look at the content of our directory. And so what we see now is that we have this file name that looks how we would expect. And so now if we type in head DCS star, and maybe also add a TSV at the end, so we don't get the sumstat, because then we have the compressed sumstat in our head command. So I did something wrong. Oh yeah, not looking good. Well, so yeah, and so now we see that we have generated the PRS for the 1,000 genomes dataset that we generated, that we downloaded, and we have our weight files, which obviously aren't going to be very good weights or good PRSs because we have only ran the algorithm for 4 iterations, which is not nearly enough. So in this case, we are actually doing some of the work on a more beefy Google Colab instance. So if you just run this natively, basically if you copy what I've done thus far, and if you now type in mproc, you will generally see a much smaller number. So there will be only 2 cores available, which is fine. We'll finish the example, but will not finish the full procedure in a reasonable time, which I will be doing right now, and pause the video and show you that, if you have many workers and many cores, the procedure can finish in a reasonable amount of time. So then that also concludes this basic tutorial and gives you an idea of what you can do with this tool, how much time it would take you, and what's needed to run it. So let's see. Let's go up and run this command again. But now we'll be removing and iter. And if we then hit enter, we'll also see that it gives a warning that now, since the output file is going to be the same, that if we wait and have this finished, that it will overwrite the previous file. So just a little extra thing that I put in to make sure that you're not accidentally overwriting files. Also, like under the hood, when you run the tool, a small file will be quickly saved and removed to make sure that the location where you want to save is actually there and that everything works before you basically run this whole procedure, and then after the fact, have it not be accessible. So basically, like for instance, a directory that wouldn't exist, or the particular location is a read-only location, the output location. So now I see actually that I forgot to specify an important option, being the number of jobs, which we now would like to make much bigger than 22. So let me see. So that's better. So now under the hood, 22 cores will be working on 22 different tasks, meaning that it will be done in approximately half an hour. So just a little bit of a background on these progress bars. So the first numbers are the amount that the particular procedure has been running, and then the number afterwards is how long it thinks it still needs to complete the whole progress, basically to finish the task at hand. And so with that, I will be saying bye to you, and you'll see that in the end, it finished the whole training of the PRS and generating the predictions in a reasonable amount of time. Cheers. Bye. Time fast forward. And so when I was waiting for this procedure to finish, I realized I forgot to tell some trick. So in case it was not straightforward for the tool to find like the relevant call mapping, you can just go ahead and copy the error message like so and dump it into a chatbot, and the chatbot will give you the correct call mapping, which is nice. So that's something I wanted to make you aware of. And it is done in 45 minutes, as you can see.